can I say? Anyway, so we have conservation of linear momentum. The total linear momentum at any instant must be equal to 0. So as the lumberjack starts walking, I add the linear momentum of the lumberjack plus the linear momentum of the log. And this must be using velocity relative to the shore. That's why it is mass of lumberjack times by an unknown velocity. The 2.7 is relative to the log, not relative to the shore. Okay? So I have to put 85 times velocity of lumberjack relative to shore plus, now the other one is the log, which is 380 kilograms. Mass times by the velocity, and I'm going to call that log relative to the shore once again. Okay, everything relative to the shore. And this must sum to 0. Right? They tell you ignore friction between log and the water. That's what I mean by no horizontal forces acting. Now, I think I went through this rather quickly, and I told you it's all vectors. And what you find is that it's very simple, actually. The vector relation for relative velocity is the velocity of anything relative to something else is equal to the velocity of the log relative to, of the lumberjack relative to the log plus the velocity of the log relative to the shore. You see, these two on the in the origin are on the outside, and then you've got log in between. You can substitute log for anything. It could be bird, it could be moon, it doesn't really matter. Okay? So here you've got 3 possible quantities, that's all. So you have to talk about velocity of something relative to something else. So if what they want to do is to find the velocity of the lumberjack relative to the shore, this is what they want to find, right? Velocity of lumberjack relative to shore. So in this first equation, I'm going to get rid of velocity of log relative to shore. Okay, so from this equation, the second equation, v sub log relative to shore is going to be equal to v sub ls minus v sub l log. Okay? So I'm going to now in here, I can put down the vector sign. If you want to, you can just put down the vector sign. In one dimension, sometimes you ignore the vector sign, knowing that to the right is positive and to the left is negative. Anyway, so what we do now is we can substitute this into this equation, and you have 85 VLS plus 380 VLS minus VL log. This must be equal to 0. And what you are given, so from here, if you simplify, you have 85 plus 380, so that is 465 VLS, and minus 380 VL comma log, which I bring to the right-hand side. 380 V sub L log. Now, that is what is given to you. That's the 2.7. You read the question, it says the velocity of the lumberjack relative to the log. So this is 380 times by 2.7. So from here you can get the velocity of the lumberjack relative to the shore to be 380 times 2.7 divided by 465. You work it out, you will get 2.2 meters per second. Now, so this is just an application of conservation of linear momentum. The complication, the difficulty only is in treating relative velocity. So I won't ask you on that, but I'll just show you this because it's interesting. But you can see if the lumberjack goes to the right, the log will move to the left. You had a question?
Yeah, could you bring it down a little bit, please?
Bring what down?
The two were matched up together.
The whole question, you mean?
Oh no, see how when you pushed up, it matched up with the first line, with the bottom line? See how, okay.
It's difficult for you to see now. Yeah, something like that. What's that?
They want the back to be the white so that they can see the variations.
Wait, you want me to move up?
Move it up so that they can see.
Okay, so we don't, like that?
Yeah.
Okay. Now, one of the interesting applications of conservation of linear momentum that's described in your book is the so-called ballistocardiograph. And they have an interesting story about how in Tennessee prison escape, the prisoners got on the laundry truck, and after that they installed this system, the ballistocardiograph, and now you can, without opening up the truck or anything like that, can detect heartbeat. So the idea is when your heart is pumping and is pushing blood out through the aorta, whatever that is. I last had biology, you don't want to know. 40 years ago, jeez, I'm too old. Anyway, when you push blood out one way, conservation of linear momentum would mean that, you see, you are imparting linear momentum to the part of the system, blood, in one direction. So if the total linear momentum is to be conserved, if you start out before the pumping, right, they are both stationary, then your total linear, to a good approximation, your total linear momentum is 0. So when you push the blood down, then your body would recoil. And it is this recoil that would cause your body to move in the opposite direction. And if you have a very, very sensitive force meter, you can detect it. And they can make force meters very, very sensitive. So this is how they can detect your heartbeat, just by even putting it against the truck. They can detect that tiny, tiny little motion, and they can know whether or not there's someone inside. Recoil is very, very common. If you ever fired a gun before, anyone here has done it? Not me. Never touched firearm in my life. But if you ever fired a gun, and I know because I know physics, when you fire a gun, okay, before the bullet flies off, the system, which is you holding the gun and the bullet, they're both stationary, total linear momentum 0. When the gunpowder explodes and it sends the bullet out, it acquires linear momentum that way. Therefore, if the total linear momentum is to be 0, you and the gun must recoil in the opposite direction so that being vectors, they add to 0. Now, of course, the bullet is much less massive, so you have very high speed, but still small momentum, so that you only, because of your large mass, you only need to move back with very low speeds. Okay? If you want to see a dramatic effect of this, you go join the Navy, see the world, and then when they fire this, I do not know how many inch cannons all at once from the battleships, the whole battleship can recoil and can move backwards, opposite to where you launch your missiles. That's dramatic because those are very big and very fast. Anything else, bullets that you, from a gun or from a rifle, all of those things. So you see pirate movies when they fire the cannons. You know what? If you go to forts, you would see the cannons are either bolted down or actually they rest on something that can slide back because they have to recoil. All of that is a consequence of conservation of linear momentum. Okay, I'm going to go on to the next two topics, which is collisions. There's an interesting section, there are two interesting sections. Variable mass, I'm not going to talk about it. But center of mass or center of gravity, I will come back to it when we go to chapter 11, because that's important over there. Okay, so we're going to talk about collisions. Collision is the name given to when two, if you want, or more objects strike one another. And we are going to call it a collision because we are only going to consider cases where the collision time is so quick, you can ignore all external forces that are acting during the collision time. Okay, that's actually a point that is not well appreciated, because a lot of the times when people do problems, and as I'll discuss, they only see from their everyday experience what happens after. Okay, and after is affected by friction and whatnot. What they refer to is that very short interval when, it's way after collision already. The collision happens when my two fists are together. So can you see how fast that occurs? So after the collision, you're subject to other forces, and the motion will be governed by those forces. We're not interested in that, because presumably we know what to do. We are only interested now in what happens during the collision time, during that short time interval. And what we learned from the previous time is forces act for a very short time. There's an impulse, force times time, average force times time, right? And what does impulse equal to? What's that?
Momentum?
Not momentum. Not quite, almost. Change in momentum. Okay? So that's the important thing. So they say time of collision short, you ignore external forces, and therefore, by definition almost, a collision is one where linear momentum is conserved. Okay? So this is the important thing. Now, we are going to consider two kinds of collisions, or two classes of collisions. One that we call inelastic, and one that we call elastic. Now, most collisions are inelastic. Most collisions in your everyday lives are inelastic. And by that, we mean linear momentum is conserved. So when I tell you it's an inelastic collision, I'm also telling you linear momentum is conserved, but nothing else is conserved. Okay? Now, within this inelastic collision, there is a special category that's called completely inelastic collision. That's just another of those terms where if I tell you it's completely inelastic, it means that the two bodies that are colliding, they like each other so much, they stick to one another. They become one body. Okay? So only linear momentum is conserved, kinetic energy is not conserved. In the previous one, you see that this one is not moving, right? But what if it is moving? And in fact, I don't care whether it's moving to the right or to the left. If it is moving to the right with 2 meters per second, what is V2 initial? Positive 2 meters per second. If it is moving to the left at 2 meters per second, V2 initial is minus 2 meters per second. Okay? Remember that. That's very important. So when you go, okay, that's just a definition. So let's look at this example. So very simple. Completely inelastic collision is the simplest kinds of problem you can do. So this is something to a very good approximation is what happens when they want to couple cars in trains together to form a longer train. All right? They just let them collide very gently, and then they hook up as one. So this is the simplest scenario. You have a car of a train that's moving with some initial velocity. That's what this is. V sub 1 comma I means 1 refers to the first body, I means initial. And it's just some velocity it has, right? And in one dimension, it's V naught. They write it as V naught. Okay. The second body, the second car, has initial velocity 0. Now, if it's inelastic, completely inelastic, what that means is they couple together, they become one object, one long car after the collision. So they move together as one, and they have one velocity, which we call V sub f. All right. So when this is the case and you apply conservation of linear momentum, it's very simple. All you're saying is, I know the linear momentum at one instant in time. I know the linear momentum at all other instants in time. So in particular, before the collision, we always draw something before. The linear momentum is m1, the mass of this first car, times by its velocity, v naught. Now, I don't like this, but I'll do it. Remember, velocity is always a vector, so is linear momentum. But in one dimension, it's very common to leave out the velocity vector notation. Then it's implicit. If it is moving to the right in the positive direction, it's v naught is positive. If it is moving to the left, then v naught will be negative. You've got to put that in. Okay? All right. So this is the linear momentum of car 1. What is the linear momentum of car 2? 0. Okay. So that's the total linear momentum before collision. What is it after collision? You look at it, how many bodies do you have after collision? 1. What is its mass? Well, you don't necessarily know that they have the same masses. So I call them m1 and m2. And they both move with velocity v sub f. That's it. That's the statement of linear momentum conservation. What you use will depend on the problem. If I give you m1, m2, and v naught, I can use this to find v sub f. I can give you m1, v naught, and v final, and I can use that to find m2. Okay? So it's not used to find one or the other. It's just a relationship. And you just use it to find whatever you need. You find that if both m1 and m2 are moving, then in one dimension, the total initial momentum is m1 times by the initial velocity of v1 plus m2 times by the initial velocity of m2. And remember, v sub 1, comma I and v sub 2, comma I can be positive or negative. Okay? Algebra takes care of it. We just leave it as a positive quantity. And if in the end I solve, for example, you give me all the quantities and I solve for v final. If v final is positive, the two bodies that are coupled together after the collision move in the positive direction. If it's negative, they are moving in the negative direction. Okay? So this is total linear momentum before collision. And since they move together as one body, that's the final total linear momentum. And you equate these two, and you solve for v sub f, you will get this. Okay? I mean, students would like to write down the formulas in their formula sheet, but they all follow from conservation of linear momentum. And you will need to know how to apply that, because not all cases are going to be one where your object is stationary, one is stationary, the other one is moving. They're quite simple to apply, so you should just learn to apply it. Now, this is an example that's done in your book. It tells you that you have this is called ballistic pendulum. This is actually how they figure out the velocity of a bullet that is shot out of a gun or a rifle. That's what they call it, a ballistic pendulum. And many of you here watch CSI shows and they talk about ballistics. That's the ballistic of this. All right. Now you actually do this experiment in your lab. Have you done that? Well, maybe you have. Oh, you're doing it this week. Now, in the example in your book, they say you can use this. If I give you V0, you can use it to calculate H. In your lab, you actually do not know V0. You fire it, you weigh the masses, you measure the final height, and you use that to figure out the initial velocity. That's why they call that the ballistic pendulum, because you use that to figure out usually they fire a bullet. So it's very simple. You see, you have this pendulum bob that is sitting there. It's got mass m, 0 velocity. You fire a bullet and it gets stuck inside. So after the collision, the two objects are together. And they will have some final velocity, which is called v sub f. Now notice that when they draw it, the pendulum, this thing, hasn't swung yet. That's because your collision happens very quickly. It only imparts a velocity to it. It doesn't move during the time of the collision. That's a very good approximation. Okay, it will move ever so slightly, but we can ignore it. So in this collision, it's a completely inelastic collision, and you can use conservation of linear momentum to figure out what the final velocity is. So if you look before collision, the linear momentum of the system is little m times by v0 plus 0. All right, the pendulum bob has no velocity. This must be equal to linear momentum after the collision, which is this thing. Now it has acquired a total mass of little m plus big M, and it is moving with some final velocity v sub f. So very quickly you can figure out what v sub f is. Right? It is little m over little m plus big M times by v sub 0. Now, of course, if you give the pendulum bob a certain velocity, it's not going to sit there. It's going to move. Now, you can ask, what happens, what kind of motion do we have? They tell you, use conservation of mechanical energy. Now, can we actually understand that? If you look at the forces that are acting, right, you always have gravity, which is a conservative force. And then as you move, right, this is the arc that it moves through. Because it is tied to this rod or to this string, there is a tension force. So there are two forces acting. How can conservation of mechanical energy come about? When the work done by the non-conservative force equals 0. So you don't care about the weight because that's a conservative force. But what about tension? Well, because you move tangent to the path, your tension force is always perpendicular to your direction of motion. Therefore, the work done is always 0. And therefore, mechanical energy is conserved. So if I want to use conservation of mechanical energy, then I say this is my starting point. It has, and if I call that my 0, U equal to 0, okay? Then my initial mechanical energy, which is U0 plus K0, or sometimes I call that I for initial. This must be U final plus K final. Now U initial, if I choose that to be my zero of potential energy, my initial kinetic energy is 1/2 the mass times by its velocity. This must be equal to U final. Now what is U final? Now U final, you have, this line here is the zero of potential energy. You have gone up. Your potential energy is mg times by the y final. Y final would be h, because you call y 0 here. Okay? Therefore, that is your final potential energy. And by definition, you move until you stop, which is you have zero velocity. Therefore, you have zero kinetic energy. Sorry, this is not m, but big M plus little m, right? It's the whole mass. And you notice that the masses cancel, and you have that V final squared is 2gh. So there are two relations here, and depending on what you want to solve for, you can figure out whatever you need to figure out. For example, in your lab, you want to find V naught. You just substitute Vf into this equation and then solve for V naught. In the text, they want to solve for H. So all you do is you look at this and you say H is V final squared divided by 2g. And V final is this. So you square that, divide by 2g. That's your answer for H. Okay, so it's just go back and do the algebra if you have to. But the application of conservation of linear momentum, conservation of mechanical energy are what you need. Okay? All right, let me. Now, inelastic collisions can happen in more than one dimension. In 2 dimensions, what is different? This is where the vector nature becomes very important. All right. Now, this is an example in your book. You have 2 cars, this one and this one. They are moving towards the intersection and they collide. And this is what they call the completely inelastic collision, because the 2 cars stick together and move as one after the collision. And all you have to do, because this is a completely inelastic collision, the only thing you have conserved is linear momentum. So you use this. P1 final plus P2 final is equal to P1 initial plus P2 initial. Now in 2 dimensions, because they are vectors, what do you do when they are vectors? The same thing over and over again. You just look at that one equation and write down 2 equations in 2 dimensions, right? One for the x component and one for the y component. And once you do that, then it's a matter of solving. So I think in this case, you have 2 equations, right? You put P sub 1 final x component plus P sub 2 final x component equal P sub 1 initial x component plus P sub 2 initial x component. If you look at this picture, what is the x component of linear momentum for car 1? It is just m1 times by 16. What is the x component of car 2? 0. It's got no x component. So conservation of linear momentum x component means I look at the x component of car 1, which is this, plus the x component of car 2, which is 0. That is the total linear momentum x component before collision. I must equate this to the x component final. Now, final, the two cars move together. Look at this drawing, right? They move together with this velocity, which they call v sub f, at an angle theta with respect to the x-axis. Therefore, what is the x component of linear momentum after collision? Well, it will be the magnitude, which is m1 plus m2 right, times by the velocity, which is the speed would be v sub f. Now, if I put in the vector, then I put the vector. If I want the x component, what is the x component of v sub f? So you can see this is cosine theta here. Okay, so you have one equation. You do the same thing for the y component, which I'm going to do quicker. The y component would just be m2 times by its velocity, which is positive, it's upwards. This must be equal to m1 plus m2 v sub f. The y component would be sine theta. Now, if I give you the masses of the car, so m1 and m2 are known. The unknowns would be the final velocity and the angle. Okay? So from here you have two equations, two unknowns you can solve. How you solve it may be challenging to some of you. Like I like to pacify people, you write those two equations down correctly in the final exam, 90%. I don't want you to solve it necessarily. That's math. I'm not teaching math in this class. Okay? If you have time, you can go back and try to solve them. Okay, now, if you want to use this in analyzing a car accident scene, you can, you look at the cars, you know the masses. You estimate, you add the passengers, you look at them, oh, that's about 120 pounds, about 200 pounds. You know the masses. From the point where they collide and where they end up, you can estimate what the final speed is. You know the angle, you know the final speed, you know the final velocity. From here, you actually can figure out the initial speeds of car 1 and car 2. So you don't even have to ask them, are you speeding? We can work it out. And then we know which one is the one that was speeding. Anyway, doesn't matter. Okay. I don't have time to work this out all that much, unless I do it very quickly. You want me to do it very quickly or not at all? Tell you what, I will work them out and put it out on YouTube later on today, but I'll do it very quickly here so that those who can follow would do it. 28, a cart of mass m moves with a speed v on a frictionless air track and collides with an identical cart that is stationary. If the two carts stick together after the collision, what is the final kinetic energy of the system? Very simple, straightforward problem. Now, whenever you do this, I always draw. Maybe it's because I'm very visual. I don't know. All right, so you have two identical carts, so they have identical masses. This one moves with speed v to the right. I'm going to do that. And this one has zero initial velocity. After the collision, they stick together, and you have some final velocity. Question, what is the final kinetic energy? Well, if I want to find the final kinetic energy, I have to find the final velocity. Because the final kinetic energy is 1/2 times by the mass, which is 2m, times by v final squared. Right? K final is 1/2 2m v final squared. So I've got to find v final. Now, how do I find v final? I use conservation of linear momentum. Momentum before impact is m times v plus m times 0. That must be equal to 0. And my momentum after is the total mass, because there's only one body, total mass 2m, v final. And you can divide both sides by m, and you get that v final is 1/2 initial velocity, initial speed. Therefore, k final is 1/2 2m, 1/2 v squared. And if you work it out, this is equal to 1/4 mv squared. Now, the reason I want to work through this is, what is the initial kinetic energy? Initially, it is 1/2. Only one of the masses is moving, so m is m, and it is moving with speed v, so it's 1/2 mv squared. And what you notice is that you end up with 1/4 mv squared. You started out with 1/2 mv squared. That means you have lost kinetic energy. What happens to the kinetic energy? You didn't convert it into potential energy. So this is what they call lost, or if you want, it is converted to other kinds of energy. In a collision in a car, it will be energy that is used up to do work to dent your car or to crush your car. It is also used up, if you go touch a car after collision, it is harder. It's the same thing with a hammer. When you use a hammer, you knock, you pound on the nail. At the end, if you touch the head of the hammer or the nail, have you done that before? It's hot, okay? And heat is a form of energy. So some of the energy, the kinetic energy of your hammer, is lost or converted to heat. Now, when you hit, we actually have a problem like that. I will work out number 32. Okay, this one is so simple. I want to see how many of you here can work it out. A box slides with an initial velocity. Look at the diagram, right? V initial, which is this quantity, is 10 meters per second. It's on the frictionless surface, collides inelastically with an identical box. So same mass. Now, the boxes stick together after the collision. What is the final velocity? Now, you have to assume that this one is stationary. It doesn't draw as if it is moving. So this is a simple problem. Everyone has that picture? I'm going to start the poll now. Work out what the final velocity of the two boxes are that are moving as one. Okay, I'm going to move to PC so you see the question and the answers. All you do is you look at linear momentum before collision, linear momentum after collision, equate them, and solve for what you do not know. I should have given a slightly different problem. done. I'm going to turn it off now. Wow, we have answers from A, B, C, D, and E. Ten, 9, 8, 7, 6, 5. Are we done? Okay, I'm going to turn off the poll now. Okay, you just have m times v equal to 2m times by v final. So you should be able to solve that out very quickly. Let me see, I need to go back to here. Okay, the other topic we're going to cover is something called elastic collision. And as I said before, in addition to linear momentum conservation, kinetic energy is also conserved. Now, the book starts out very slow, gives you the simplest scenario, which is you have an object mass m1 with velocity v sub 0 to the right, and m2 is stationary. And they say that after the collision, after the elastic collision, we don't know how they would move. Now, that's the beauty of algebra. When you don't know what they are, you just represent them by unknowns. So m1, after the collision, will be moving with velocity v sub 1f, and m2 will be moving with velocity v sub 2f. Notice I call them velocity. So they can be positive or negative. I draw them as positive, so when I work out the answer, and my answer is negative, what does that mean? They are moving in the opposite direction to what I have chosen. Okay, so that means in this example, if it happens to be that I work it out and v sub 1f is minus, it means that it's not moving to the right anymore, it's moving to the left. Okay? All right. Yeah, this relation I showed you, right? I said all you do is you apply the two equations, conservation of linear momentum, conservation of kinetic energy, and solve, you will get this. The conservation of linear momentum will give you m1, v1 initial, they call that v0. And then plus 0, this must be equal to, after the collision is m1, v sub 1, comma f, plus m2, v sub 2, comma f. Those are the final velocities of 1 and 2. Okay? That's conservation of linear momentum. You are told that kinetic energy is conserved, so 1/2 m1 v sub 0 squared. The second body, m2, has 0 initial kinetic energy. And then you have 1/2 m1 v sub 1 final squared plus 1/2 m2 v sub 2 final squared. Now, when you have two equations, and if the two unknowns are v sub 1 final, v sub 2 final, you can solve them. How do you solve them? Algebra. You go through the algebra. What do you get as the answer? Well, here you go. They tell you the answer. All right. Now, if you want to, you can go back and work it out yourself. It's just a little bit of algebra or a lot of algebra, depending on your perspective. But you can always write this down, but you have to realize that this applies only in the case where You have M1 moving, M2 stationary, and then they collide, and after that they both move. Okay, you get this answer. Now, a bit about the way to do this. Okay, if you would have the situation where M1 is moving with this velocity and M2 is moving with this velocity. Now I draw both of them to the right, so I just write them down there. When you work things out, and if I give you the problem, I say M1 is moving to the right with speed 2 meters per second, and M2 is moving to the left with speed 3 meters per second. Then in the formula that I end up deriving, V sub 2 initial is minus 3 meters per second. Okay? All right. So you have the same scenario. You have one object moving with one initial velocity. It collides with another one. And after the collision, they move like this. And once again, I do not know what they are. I call them V sub 1f and V sub 2f, respectively. And I choose them to be moving to the right. Same thing, right? If I end up working out the answer to be negative, it means they're moving to the left, that's all. Now, when you do this, you would know that in a realistic situation, your V2 final can never be negative. Because when you collide, it can only move to the right. How can it ever move to the left? It can only move to the left if M1 goes through it. And that's not the kind of scenario that we have. All right? But when you work it out, it will work. So once again, you have two equations and two unknowns. The algebra is a little bit more complicated, which is why they put it in problem 91. And I'll give you the answer. The answer is this, and I even write it in vector form. Number 91 doesn't write it out in vector form. But implicitly it is, because both your V1 initial and V2 initial can be positive or negative. Okay. Now, what is not even stated, and which is still true, is this relation holds true even in 2 or 3 dimensions. I'm not even going to touch on that in any problems, but they're just generally valid. They're vector equations. You can get rid of the vector sign if you want, if you're working in 1 dimension. Okay, now, how do we apply this? This is actually something that is mentioned in the tiny little section in your textbook that says, something like the relative speed of approach before collision is the same as after collision. Yeah, don't bother with that. That's what they mean by this. Now, in the sample exam, you actually have to use this. And that's what makes it very tough. I don't know. I don't think I'll ask a question like that, because I think 90% of people won't be able to solve it. But I'll show you how to use this. Okay. So let me write it out here, which is V1 initial minus V2 initial is V2 final minus V1 final. Okay. Now, this is true for all elastic collisions. Anytime you have an elastic collision, consequence of this set of equations. So that's why I call it revisited. Didn't have to move back. But anyway, when you have M2 stationary, so this is M2, it is stationary. M1 is moving with V0. Okay, this is before the collision, and after the collision, M1 is moving with V1 final, and M2 is moving with V2 final. Like I said, when you solve the two equations for V1 final, V2 final, this is what you get. Now I want you to look at the equations and see what happens if M1 equals M2. What do you notice about V1 final? If M1 equals M2, what is V1 final? 0. It says, what that says is that if I have M and M, same mass, M1 equals M2, they're both the same. This one is stationary and this one is moving with velocity V0. When it collides, if it's an elastic collision, what happens to this one after the collision? It stops. How many of you here play billiards? Head on, I mean, you hit it straight on. Do you notice this before? It stops. They're almost the same mass there. And the second ball moves off. Let's see what speed the second ball moves off with. If M1 equals M2, what is the final velocity? What is the final speed V sub 2F? What's that? V0 is the same. So it's actually more special than that. You come in with 5 meters per second, you bang on this, you stop, this one takes off with 5 meters per second. That happens in elastic collisions. And I forgot, you see, there's this toy, I think you have all seen it in movies, where they have like 5 balls, steel balls, hanging down. And then you lift one end and you release it, and it collides. There's a collision, and then what happens at the other end? It rises. That is an example of an almost elastic collision. So what happens is the first ball hits the second ball, it stops, gives the velocity, same velocity to the second ball, which collides with the third, it stops. The third acquires the same velocity as the incoming, stops, transfers to the fourth, stops, transfers to the last ball, and then the last ball rises to the same height. Then it repeats. So you go talk, come up, talk, come back up, and it keeps doing this. Now, of course, those are not perfectly elastic collision. Graduate exam, they ask this question, how do you know they're not perfectly elastic collision? Because you can hear the noise. Part of the kinetic energy is converted to sound. Okay, that's why eventually they stop. But if you have perfectly elastic collision, they go forever. Now, the book describes this. The nice thing about that is if you take 2 balls and you let it bang, how many of you have seen that? No one has seen that? I'm shocked. You're so deprived. I may have to bring it in, or you can go to YouTube and look for it. If you take 2 balls and you release it, there are 3 balls left here. When you hit this, 2 balls go up. Yeah. And then it repeats. This is only possible if both kinetic energy and linear momentum are conserved. What if you take 3 balls? You have 2 left there. Yes. This one, people may find, they're not sure. 3 balls come down, and then 3 balls go back up. You should see this. I should slap myself for not bringing it. Anyway. Yeah, I know, YouTube, you can watch it too. I don't have time for that. Yes?
So, kinetic energy being conserved is the reason why instead of 1 ball going 3 times as fast, that
Right.
balls will come back up?
To conserve both linear momentum and kinetic energy, you cannot have 3 balls coming down
Yeah, and then
and one ball moving out with 3 times the speed.
That would be just momentum, right?
That's right, that would conserve linear momentum, but if you look at the kinetic energy, they are not the same. Okay, that's what prevents it. All right. What if collision is not head-on? This is what happens in a head-on collision. If you play billiards, if you have a head-on collision, it will just stop and this will move. What if you don't have a head-on collision? Even if this is stationary, glancing. If you play, you would know. If it's an elastic collision, you can go solve it out. If this is stationary and you have a ball coming in and it's an elastic collision, they will both move off, and there's a 90-degree angle between them. Those of you who play a lot of billiards would know it at this level, in your gut. But you can prove that they are 90 degrees to one another. Okay. Now, elastic collisions, the book claims, can only be solved if some of the final information is known. And all you do to solve problems, I'll talk about that. All you do is in principle, you apply conservation of linear momentum and conservation of kinetic energy. Okay, so let's talk about the two-dimensional case. All right, you have two objects coming together. They collide. Something happens, they move off. Even if you know the mass, velocity, you know everything before the collision. After the collision, how many unknowns do you have? Well, you have two balls that are moving, right? So if you know nothing about their velocity, how many unknowns do you have? 4, right? If you look at velocity 1, you do not know its x, you do not know its y component. Or if you want, you do not know its magnitude and direction. So you don't know those two quantities for ball 1. You also do not know the same two quantities for ball 2. You do not know 4 quantities. If you study algebra, you know that if I want to solve for 4 unknowns, how many equations do I need? 4 equations. So how do you get those equations? You say, oh, one of them is conservation of kinetic energy. So that's one equation. Now, you also have conservation of linear momentum. And as I said, in vectors, in 2 dimensions, with vectors in 2 dimensions, you have conservation of x components of linear momentum. So that gives another equation. You have 2 equations now. You also have conservation of linear momentum in the y direction. So you have 3 equations. And that's it. You cannot know anything more. When you have collisions in 2 dimensions, you cannot know the answer without knowing something else about the final result, which is what this statement is saying. If some final information is known. Now, I will show you, the book has some examples. I'll show you an example, right? I'll solve these 2 out. I'll do the 2-dimensional problem. This is an example in your textbook, but different, modified. So this is problem 41 in your text. 2 astronauts on opposite ends of a spaceship compare lunches. One has an apple, the other an orange. They decide to trade. Astronaut 1 tosses the 0.13 kilogram apple toward astronaut 2. So this is what happens. Astronaut 1 is here and throws an apple towards astronaut 2, who's over here. So the apple has a mass of 0.13 kilograms, and it has a speed of 1.11 meters per second. Now, astronaut 2 has an orange that he or she throws in the other direction. The mass is 0.16 kilograms and is thrown at a speed of 1.21 meters per second. So assume that the positive x direction to be the initial direction of motion of the apple. So this is the positive x direction, right? This is the apple. Okay, now unfortunately the fruits collide, sending the orange off with a speed of 1.03 in the negative y direction. So this is not a head-on collision. This is what happens in 2 dimensions. What that means is after the collision, the orange moves off in the negative y direction with a speed of 1.03 meters per second. So the apple is now completely unknown. You have no idea how the apple moved. That's what you're supposed to find out. Assuming the collision is elastic, what are the final speed and direction of the apple? That is, they want to know 2 quantities. Its speed and direction, or if you want, equivalently, if you know its x and y components of velocity, you would know its speed, its magnitude, you would know its direction. Okay, we're back to vectors once again. So I'm going to draw the apple, and anytime you do not know what it is, this is your apple, you just say it has some velocity at some angle. Now, instead of talking about v and theta, I'm going to work out its in terms of its x and y components. So the apple moves with some x component, v sub x, and some y component, v sub y. Okay. Now you are told in this problem is an elastic collision. You only need to find these 2 unknowns. You only need 2 equations. How do you get those 2 equations is up to you. You can use the x component of linear momentum conservation, y component conservation, kinetic energy conservation. You can use any 2 of those 3. Okay, you can go back and work out a different way. I'll work out and tell you, I'll work out in terms of conservation of x component of velocity, of momentum. So if you look, initially the apple is moving to the right. So conservation of x component of linear momentum would be x component of apple mass times velocity plus x component of orange, which would be mass times velocity. Now, the orange is moving in the negative direction. So you have to put minus 1.21. Okay? This must be equal to the x component of momentum after the collision. What is the x component of momentum of the orange after the collision? Now, this is after the collision. This is the orange. What is its x component? 0. That's good. Now, all you have to do is to say, what is the x component of linear momentum of the apple, which would be the mass of the apple times by the x component of its velocity, which is the unknown. Voila. I have one equation here, and the only thing I do not know in this equation is v sub x. And you can solve for it, and it turns out v sub x is equal to minus 0.38 meters per second. What does the minus sign indicate? See, when I drew it, you see how I draw it this way? When I solve it and it's negative, it really means its component is pointing in this opposite direction. Okay? Now, I've run out of time. You can go back and do this. You do the same thing for the y direction. And what you find is that you can get immediately what v sub y is. And v sub y works out to be 1.268 meters per second. And once you know the x and y component, you would get the magnitude and direction. Now, if you ask, why haven't I made use of the conservation of kinetic energy, as this is an elastic collision? The answer is you can. If you actually make use of conservation of kinetic energy, you would work out the magnitude of the speed in one step. Here, to get out the magnitude of the speed, you have to take the magnitude, the square root of v sub x squared plus v sub y squared. If you use conservation of kinetic energy, you get that in one step. But the angle is a little bit more difficult. Well, it'll take another step, a different way of doing it. Okay.